So my name is Doug Hatfield, and I am head of sales here at Flexcompute, and I'll be your host for this webinar today. Very excited to bring to you this information. Hopefully, you'll find it interesting. We've got two distinguished panelists who will present material on Tecplot and on Flexcompute. First panelist is Jared McGarry, sales engineer at Tecplot. Jared is from the University of Washington with a bachelor's in mechanical engineering. He works with Tecplot users who are academic, commercial, and government organizations by teaching them how to use the software and how to respond to their questions and addressing technical needs and concerns. And I'm sure you'll find his material interesting. The other panelist we have is Dr. Roberto Delorata Rinaldi. He's Italian. He grew up in Molfetta, and he's been doing aerodynamic engineering for his entire career with a PhD from University of Turin with collaboration with ECL in Lyon. He then got into motorsports, moved to the UK, where he worked for Williams and Williams Consulting. He also worked for McLaren, where he did work on the Ultimate Series, and then finally spent some time in Formula One with Aston Martin. And now he leads all of our automotive CFD engineering for Flexcompute as a senior automotive application engineer. Next slide. So this will be our agenda today. I'll talk for a few minutes on the introduction of Flow 360 and why we are involved in the automotive industry. And then we'll have a hands-on demonstration from Tecplot and Flow 360. We'll get some experience with expert insights into automotive CFD optimization from Dr. Rinaldi, and then a case study on NEO and our efforts with NEO and the future of aerodynamics and EVs, and then we'll wrap up. Next slide. So I'll begin with why CFD matters for the automotive industry. What challenges do you face and do automotive engineers face, and how does CFD and GPU-enabled CFD support that? So clearly one of the challenges is shorter development cycles. What you're finding is all of the OEMs are trying to innovate faster and faster, proliferation of models, proliferation of mid-cycle replacements. We're seeing this across the industry, whether you have EVs who are new companies, new entrants. And so there's a need to continue to increase the speed with how you get your answers and what you do for optimization. The design complexity is increasing, right? So you've got more different powertrains. You have now different requirements for autonomous and driver assist. All of these things are adding, more challenges from aerodynamics and thermal management and aeroacoustics. Cost pressures, right? CFD can be very cheap, can be efficient. It's much cheaper than physical test, but we need to continue to reduce cost, reduce time, and continue to drive innovation, into the CFD industry. Regulatory compliance. There's increasing pressure to have stricter emission cycles. There's increasing pressure for improving efficiency, making sure that you meet the requirements of the regulatory bodies, and CFD can support that. All of the companies that we work with, all of the automotive industry is going through a digital transformation, looking at, what are they using for PLM? What are they using for simulation tools? What are they using for CAD? They're trying to transform to have a complete digital twin so they can understand how the models are behaving, how the models are performing, as they're designing them. And CFD plays a critical role in that. And finally, global competition. There's increasing need to iterate faster so that you can validate and stay relevant in the industry as you move from the different regions and for the different competitors. Next slide. So we believe that the industry needs fast simulation. You can see here the trend in crash simulation, what started in the 80s and how it's progressed in terms of model size as you go from the 80s to the 90s and so forth to current day. Models are getting bigger, runs are getting longer, and what you need is the ability to run faster so that you can increase the throughput that you get per day, per month, per year. And what you're finding is that as these models have increased, there's a gap between how long it takes to get your answer and when you want the answer. And that gap is increasing as the models increase. Hence, we see the opportunity for 100x speed up when you start moving away from CPU to GPU. Next slide. So this is an example that we can share, from work we've done in the aerospace industry with AIAA, where you can compare the simulation time for these models. This is around a 20 million cell case. It's against the traditional solver from NASA, which is well known in the industry. And this particular model will take almost 10 hours to simulate. Using this NASA solver on CPU, we can reduce that down to 3 minutes using GPU. So it's a massive speed up that you can get if you start to work with GPU-enabled CFD. And the computing costs come with it, because now what you have is a much, much cheaper computing cost, because you're only running for minutes on a GPU versus running for hours on a CPU. And we can also provide similar capability for for electromagnetics and for photonics, is in the second example below, but we're going to focus on the CFD capabilities today. Next slide. The technology behind Flow360 came out of MIT. It was DARPA funded. It was research that was done to how do you integrate the technology into the chip so that you can get low latency, maximum scalability, and maximum efficiency. There's been quite a bit of research. There's been a number of universities involved, several publications. The company has been around for now 10 years, and the team is several team is very heavy technology PhD to support building this for you. And what we're finding is that the scale up on CPU is starting to plateau, as you can see on the graph on the left. But what we're finding with GPU is it's just beginning. We're seeing doubling of speeds every 2 years, and currently no end in sight. And this means that you'll continue to get faster and faster turnaround for your cases as GPU becomes more and more mainstream. Next slide. The core solver is fundamentally Navier-Stokes fully compressible solver. It has all of the key features that you need: porous media. It has different solver options, whether it's RANs or DDS or ZDS. We can solve air acoustics because we have a low dissipation scheme. We have thermal capability in the solver. We have the ability to handle certain types of rotational needs for both the automotive and aerospace industry, whether that's MRF or sliding interface. And we have a variety of turbulence models. We lean heavily on Spalot Alamars, as Philippe is part of our is a consultant for our company, but we provide other turbulence models as needed. And we offer user-defined dynamics, so the ability to include in your simulations, looking at dynamic coefficients. Next slide. So it's a full solution for automotive. It's a native to GPU, where we're providing significant speed up. You'll hear more about that today. It's scalable, which is one of the benefits of Flow360, because it was fundamentally architected to scale well on GPUs. So we see no limit. Currently 64, 128. It doesn't plateau. Fully compressible Navier-Stokes, variety of turbulence models to meet your needs for RANs or for DDS, and versatile applications. Certainly we can handle automotive applications, aerodynamics, wind noise, various things that you would need to support your development process. Next slide. And with that, I'm going to hand it over to Jared to talk more about Tecplot.
Thank you, Doug. Roberto, next slide. Hello, everyone. My name is Jared McGarry, and I'm a sales engineer at Tecplot, and today I will be showing how our tools fit into your workflow with Flow360. So for those who may not be aware, at Tecplot, we are the leading software developer for providing visualization tools for CFD simulation data. So we've been in the CFD business since the mid-1980s, and our focus is on empowering engineers to visualize and analyze information in large, complex data, and to then communicate the results of simulation and test results in high-resolution images and animations. So our two main tools for CFD visualization are Tecplot 360 and field view. And today I will be focusing primarily on Tecplot 360 because Flow 360 outputs to the proprietary SCL format for Tecplot 360. And there is a way to bring in Flow 360 data to field view with a couple extra steps involved, and this process will be streamlined in the future. But most of what I will show today is of Tecplot 360. However, both Tecplot 360 and FieldView have data loaders for most CFD codes so that when you are benchmarking your results across multiple solvers, you can have a consistent post-processing workflow, even if the source of your simulation data changes. And today I will be explaining how our tools specifically help you with visualizing Flow 360. When you are able to create large data very quickly and efficiently with Flow 360, you need a post processor that can keep up so that the time and cost savings continues across your entire CFD workflow. And there are several ways our tools accomplish this. For handling large data, Tecplot 360 does this with the SCL format for efficiently plotting large volume data, and I'll go into more detail about that in just a moment. FieldView does this with MPI parallel and a robust client-server architecture. And then more recently, both Tecplot 360 and FieldView are getting a new graphics engine for faster rendering, leading to considerable speed improvements, especially for large and complex data sets. I'll then explain how Tecplot 360 now handles large unsteady cases. And then when you need to automate your work with Tecplot 360, you can use the PyTecplot Python API. And for those attending the seminar, we've provided activation codes for you to try out Tecplot 360 or FieldView with these new improvements. And you should have already received an email with instructions for that. But if you don't see it, check your spam folder or contact us to help you get started. All right, next slide. So how does Tecplot 360 handle large volume data? Flow 360 outputs to the SCL, or what you will recognize as the .scplt file format for loading into Tecplot 360. So SCL is an alternative data file format for improved handling of large volume data, where SCL stands for subzone load on demand. So the large volume data is divided into smaller subzones that are only loaded until a specific plot element demands it. For example, if you're drawing slices or cut planes, stream traces, or isosurfaces. So rather than loading the entire volume, you only load the regions of data you immediately need. So this leads to faster loading of the data because you are only loading the region of the data needed, less memory use when loading the data, and sometimes this can result in smaller file sizes. So the SCL format has been a part of Tecplot 360 for years now, and below is an older but still relevant example of the improvements you may see compared to working with the standard Tecplot binary or .plt file format. So for this example in the bottom left, 183 million cells loads 7 times faster, uses 93% less memory, and in this particular case, the file size was cut to close to half of the original compared to Tecplot binary. So when you're using the SCL file format, considerable performance improvements. And next slide. So as I explained, Flow 360 outputs directly into the .scplt file format, but you can also convert from Tecplot binary or other Tecplot 360 data formats to the .scplt file format. And shown here is a Flow 360 dataset that Roberto provided for us to plot within Tecplot 360. So this dataset has 243 million cells in one volume time step. And then in just a moment, we should see an isosurface being plotted in that volume that's 78 million triangles. So pretty large data set, but the performance is good in Tecplot 360 because of this file format. We're only loading exactly what we need to plot the data. So if you are working with large volume data, SCL format saves you time when loading and plotting the data. What this recording also shows is Tecplot 360 with the new graphics engine. So with Tecplot 360, you not only load the data faster, but once it is loaded, you get smooth performance manipulating the plot, even with a complicated isosurface like this. And speaking of the new graphics engine, next slide. Available now in a preview build and coming later this year in an official release is the new graphics engine for Tecplot software. So previously Tecplot has used OpenGL, but now is upgrading to use our own proprietary graphics engine using Vulkan. So both Tecplot 360 and FieldView will use Vulkan, which is faster, more memory efficient, has better long-term support, and is a good platform for modern rendering techniques like ray tracing and volume rendering. And Roberto, if you can click the video in the upper right. There we go. So here's a performance comparisons that we've done. On the left is the old graphics engine, and on the right is the new graphics engine. You can see right away considerably smoother and faster with the new graphics engine. This was conducted on a typical machine, but we can see that for certain of the plotting capabilities, much faster with the new graphics engine. The first one showed shaded surfaces about 12 times faster in terms of the frames per second. In this case, the particles, particularly particles where we have more complicated geometries or just more to render with the spherical particles, it's 15 times faster in the new graphics engine. And this third example here is showing transparency, 6 times faster in terms of the frames per second with the new graphics engine. So much smoother and a much better user experience when you have this new graphics engine. And then next slide. And specifically for field view, the new graphics engine will utilize improved PBR or physical-based rendering so that surfaces can easily plot specific materials. And so included in field view is a predefined list of materials to plot surfaces with metallic or rubber or glass or glossy or matte paint so that you can create high fidelity photorealistic plots of your simulation data. And you can see in this example, there's an option to change the background that is reflected on the surface material. So this has been with field view for a while, but it's going to be considerably improved with the new graphics engine. And then for future updates, this new graphics engine also makes possible new and creative rendering of data, such as skyboxes and environment backgrounds and plots, not just the reflections on surfaces. Texture-based vector fields visualization, for example, line integral convolution, and ultra-fast particles computation. So earlier this year, our Chief Technology Officer covered the new graphics engine in more detail in another webinar, and the recording is available on our website and YouTube if you are interested in learning more about the technology behind these new graphical improvements. And a link to that should be in the chat here. So again, this is available now in a preview build and will be in an official release later this year. Next slide. So for large unsteady cases, Tecplot 360 has you covered there as well. Available now in a beta titled Tecplot 360 MB is a preview of how Tecplot 360 will handle large unsteady data within the user interface, particularly by saving you time when you need to extract data, calculate new variables, interpolate, or perform integrations on your data set. And the way this is done is with the data journal, which displays a visual, executable, and editable record of the data operations performed to the data set within Tecplot 360. And in the example shown here, the data journal is shown on the right sidebar, and it saves the sequence of variable calculation, data extraction, and integrations for this layout to create this particular visualization and the line plot of the extraction shown here. So the data journal is only executed at time steps you visit, which saves you time by restricting the data operations to only the time steps you need in that particular moment. And then when you do need to compute for all time steps, you can hit play after your plot is set up exactly the way you need it, and then move on to other work while it crunches away. So in addition to this, zones or regions of data are organized by part names so that you only compute for the specific regions of your data set that are needed. And this new parts framework allows for unique XY line plots that can display changing variable values as they animate over time, or that are drawn as the animation progresses, that are linked with the 2D or 3D plots in the rest of your workspace. So what Tecplot 360 will allow you to do for large unsteady cases then is to prepare the plot view and analyses of your data much faster, compute only when you need to, and make the time you spend post-processing more efficient. Next slide. Thank you. So to make your post-processing workflow even more efficient, we have a Python API for Tecplot 360 named PyTecplot, which allows you to automate your work in Tecplot 360 either by connecting to an active session of 360 or by running in batch mode, including through distributed parallel processes. So you can also load any data file format supported by Tecplot 360 and then access the data directly with Python using PyTecplot. And what this does is it opens up tools for analysis of your data to include Python libraries like NumPy or SciPy, so that you aren't limited to just the analysis tools included in the Tecplot 360 user interface. And for those who are interested, we have a collection of example scripts available on our GitHub that make use of these additional Python libraries, for example, to convert data to or from unique formats, create a histogram plot, calculate an average of all time steps, and compute other statistical information about your data. or even just a script to run multiple batch operations of Tecplot 360 in parallel, exporting images for each time step of an unsteady case so that plots of your simulation are created much, much sooner. And then if you do use Python for anything else, you can integrate PyTecplot with your existing workflows. So yes, PyTecplot is useful for automating your use of Tecplot 360 to save you time, but it also expands the potential for analysis of your data beyond just the initial plotting capabilities. Next slide. Or actually, what I'll do here, let's get into a live demonstration of Tecplot 360 so we can see it in action. So here you can pause that video, Roberto, and I'll start sharing my screen.
Okay.
The video is fine, but we'll do it live.
Yeah, sure.
There we go. All right, and that should be coming through. Okay, it should look very familiar to that video, but what I have here is the same data set that Roberto kindly provided for us to test with. We've already loaded it in. It took about 10 seconds to load the data set itself, and then just over 3 minutes to plot this isosurface, but it runs very smoothly once we're loaded. Again, this is using the SCL file format. And if I want to take a look at the data set itself, if I go to data set information, let me just expand this a little bit and I go to the dataset tab. You can see all the files we've loaded in for this particular layout. We got 4 billion cells total, but again, this is over 16 time steps. So divide that by 16 to get what the total is for the first time step that we're looking at here. But if we look at just the volume zone for this first time step, 243 million cells that we're looking at here. So considerable size of data set, but again, because we're using the SCL file format, we're just loading what we need for the data set to make this plot, and we're just loading the time step that we need to get started. So Tecplot 360 is clever about how it handles large data sets of this type. But once we've loaded it in, nice and smooth rotation, translating, zooming in and out. That's also because we're using this with the new graphics engine. So even with a complicated isosurface like this, with translucency, very smooth and easy to handle once we have it in the Tecplot 360 user interface. So big benefit there. Now, if we wanted to export the results of our plot right away, we got a couple options for that. We can go to File, Export, and we can see multiple raster and vector image export options that are available to you depending on what you want to use the plot result for, whether it's for a report or just sharing with your colleagues, options for the quality of the export, anti-aliasing. If you have multiple frames, in this case, we're just looking at one frame or one plot, but we can export as many as we want on this workspace if we so choose. So if we wanted to export just the plot as a static image. We also have animation export options. If we click this drop-down menu, we can see what's available to us. For the sake of this demo, I'm not going to do a time animation, but just to point out where this is, we can click this film strip icon, and you can see multiple video export options, or exporting as a sequence of images if we want to export each time step as an individual image. And again, options for changing the quality of the result if you want to do that. Back at this drop-down menu, you can see we have animation options for these derived objects that we've created, isosurfaces. If I plot any slices or stream traces, we can export that. There's also an option to export keyframe animation, so we can stitch together multiple 3D views to make a cool 3D animation view change. All right, so if we want to do a little more analysis of the data set since it's loaded in here, we could zoom in a little bit closer to a subset of our data set, change the center rotation to where we're looking at right here. And we get an overview of the total coefficient of pressure plotted on the isosurface here. But if I want specific information at points, I can use this probe tool, left click, and then this probe sidebar will update showing the values for that surface. Again, we're only loading the variables that we need for the region that we need. So we just see the Q criterion value that this isosurface has been created at, and then the total coefficient of pressure value at that point that we're probing, and then the XYZ position, of course. And so we could copy these values if we need to use them in another equation or just copying elsewhere. And then if we wanted to add some additional plot elements to this, I've already prepped the stream trace tool here, but I can click this add stream traces, and wherever I left click, we're going to get a little bit of a load operation because again, we're pulling and loading the subzones as needed for the plot, but it doesn't take too long to then plot these stream traces. I could click and drag. Let's add it at the wake here. It'll take a little bit longer as we're loading more and more there and as we're plotting more, but it doesn't take too long. And then we can see a little bit more information about the flow in our plot. And again, still runs very smoothly as we're manipulating the plot. And maybe we want to have a closer look at the rear tire here. We could add some stream traces there, or we could place a slice. So I'm going to click this slice placement tool and see what the behavior is like just around there. Again, a little bit of a load operation as we're loading the subzones needed to make this plot, but it happens pretty quickly, and we can make quick adjustments to where the slice position is if we want. And now we get information about the total coefficient of pressure around the tire at the base there. We can use this probe tool to then probe at this slice to get more information. And you'll notice the velocity variable values have been loaded from the from placing the stream traces, so those get added into the probe list here. And then I can also make quick changes to different plot elements. If I right-click the slice here, I could change what it's contouring by from the total coefficient of pressure to something like the velocity, and it'll do a quick update, and then we can see what the velocity values are around there. So quick and easy plot changes while we're in the UI like this. So Tecplot 360 is good at making good looking plots, but it's not just limited to visualization tools. We have some analysis tools as well, and I'll point out where those are. So if I go to this Analyze drop-down menu, you can see we have this Calculate Variables dialog, which gives us a list of a predefined list of functions for calculating variables that CFD analysis may require if it's not already in your data set. If you if you don't see the variable you need in the list, or you want to use your own equation, we also have this data alter specify equations tool that allows you to use your own syntax for calculating a new variable or modifying an existing variable. And if we have equations we're using consistently, I can load that in and compute that if I'm redoing the same computation over and over again for different data sets, and then save that back out. And then back to that Analyze drop-down menu, we also have this integration tool where we can see multiple integration options: averaging, mass flow rate, forces and moments, vector averaging. So a lot of different options depending on what you need for the additional analysis in your data. And then another helpful capability when you are doing analysis is the ability to look at subregions of your data set. And so we have this option to extract from either the plot elements we've created, like the isosurfaces, slices, stream traces. We want to use zone blanking or value blanking to get to a blanked zone. And then we also have options for extracting some of those over time. So there are quite a few options for narrowing down our focus to just the subset of data that we really need. And then lastly, all of this can be automated with Python. If I go to scripting, record PyTecplot, I could just type in test.py, overwrite the previous one. But this gives me the option to now all the actions I'm performing in the user interface will get saved to that Python script. If I'm doing any image exporting, that gets saved as well. And then when I'm done, hit stop recording. I can edit that script, play it back, or use it in my other Python workflows to then automate my work in Tecplot 360, either in batch or in connected mode, depending on what I need, so that you're saving more and more time. So, and let me make one final view change. Let's see if we can turn off translucency. Take a little bit longer for this rendering change, but that's about what I wanted to show for today, just to do a live demo of Tecplot 360. This is just a quick summary of how our tools can help you when working with Flow 360. Again, when you're able to create large data very quickly and efficiently with Flow 360, you need a post processor that can keep up. And Tecplot 360 does this with the SCL data format, so you're only loading the regions of your data that you need. And Flow 360 already outputs to this format. We have a new graphics engine so that when you manipulate the plot, it is fast, smooth, and efficient. And for large unsteady cases, you load and modify data for only the time steps you need. And then all this, again, can be automated with our Python API, PyTecplot. There we go. And yeah, that's the final shot I wanted to end with. So Roberto, I'll hand it over to you.
All right. Thank you, Jared. Let me share the
Stop
screen
share.
again.
There we go.
So now in the agenda is basically a bit of live demonstration of what Flow 360 is. Flow 360 is the solver of Flexcompute, the CFD solver. So let me bring us this demo video so to give you a feeling of what it is actually. And this is the case of the drive air that you have seen plotted by Jared. So I'm gonna pause and comment here while I talk. This is our cloud environment, This is so we have two main options to upload things and to look at things. So one is using the web UI, and this is what I will share here, but also through Python API, fully scripted. And I also will give you example how to do that. So from you create a new project. So this is our web page. Then you can choose a project. In this case is a driver demo, the solver version, the units. You have different type of units you can choose. You can add a description, and then you can create basically you can start or from a geometry or from a volume mesh. We also have our in-house volume mesher. But in this case, I started from a CGNS mesh that I created, and the import file can be or UGrid or CGNS. The mesh is then uploaded, and it will be created this new project. And then you can now pause a second. You can now set up basically the whole boundary condition all through web UI or through Python. I personally prefer through Python, as probably most of engineer, because it can be scriptable, is easier, it can take trace. But so I'm gonna demonstrate here a Python script. So you have this project ID, which is unique, and you take basically when you create a project is being allocated a project ID, and then after that you have the volume mesh here, and different parameter about so here the geometry, the moment center, in this case moment length, reference area, boundary condition. So the operating condition in this case we had to match some test. So it was important to match Reynolds and Mach. But you have also standard operating condition like imposing velocity as a free stream, and then your usual alpha and beta, so incidence and yaw, temperature, as well as Doug was saying before, this is a compressible solver. So all simulation, you of course needs to specify the temperature. If you don't do it, then it will be automatically set by default of the standard atmosphere sea level. And in this case is a steady simulation. So here you specify the time stepping, and there are different type of ramp, how we speed up the solver. The best one, the optimized one, is called adaptive CFL. Is basically trying to run as fast as possible, so without diverging, and it will automatically try to maximize the CFL in trying to going as fast as possible. You get basically a ramp automatically generated, and the ramp will adapt based on the local flow condition. So you don't have actually to set up anything. The only parameter that you change is 0.25, which is the standard one. If you go lower, it will be more gentle. If you get higher, you get more stronger. But this is the recommended value. That's the only one, and then it will be automatically done. Number of steps total. So in this case, I put it 7,000. And here are the boundary conditions. So as you see, it's quite convenient. You have wildcards. So for example, here with the asterisk, you can take the whole tires, left, right, front and rear. You don't have to specify the whole boundaries. Usual wall boundary condition, in this case with wall function, so not resolved, not down to y+1. We use automatic recognition of wall function for y plus higher than 1. Sleep wall for the domain, and free stream for in and outlet. Consider we have here some turbulence quantity specified by the test case, so in terms of length scale and intensity, that of course can be set up here. In terms of the solver settings, important settings is well, the absolute tolerance, and this is the kappa coefficient is giving you basically the type of scheme you are using. In this case, I went with a low dissipation scheme to have the best representation of the wakes, so to limit the dissipation. And 033 is no other things than basically is a blended scheme between central and upwind, so it's not a pure upwind, so it is a bit more stiff, but also less dissipative. So it's the most accurate that we have, and for this case, it works perfectly in terms of convergence as well. And turbulence model. Oh, we have as well some limiter that I haven't used here. Maybe for more challenging case, you can also have limiter for velocity and pressure. Whereas I did use the low Mach preconditioner because, of course, this is a very low Mach application, being an automotive case. And on the turbulence one, I've used an SST model with the tolerance of 1 - 8 absolute. It's important to note here that the coefficient of the SST and also of the SA are all exposed. So in this case, I modified the alpha 1 coefficients, as is a usual practice in automotive, to delay the separation. So instead of having the standard default 0.31, I increased to 0.4, and that helped us in the correlation and in the correlation to experiments, basically. So this is one thing, and then in terms of output, you have the variable and the type of outputs that you want to output, and then you submit basically the Python script with just a line of command. Once the Python script is submitted, it says here then the density will be calculated because it will be automatically calculated from the state that we have imposed. And now you see that there's a tree there that has been created, and we can now load the actual analysis tool, where you can see in the web UI live the residuals, the usual quantities like CL, CD, and as well monitoring live. So all the values that you are interested in, you can see that the numbers appear. Interesting as well is that you have the CFL plot, and in this case is the ramp that I was talking before. This is more in terms of diagnostic. It plots as well the min max of velocity, omega, and so on to monitor the solution. You also have the force by surfaces, and just clicking you can remove or highlight the one that you want on CL, CD, and so on the different plots. You have CF, and then you can clearly see the evolution of the solution. So now I just pause a second here. In the simulation tab, basically, I'm going to show you how you could have set up these as well through web UI. If you're not familiar with Python, or if you're more confident with the web UI, is absolutely the same, and is very intuitive. In this case, you can see here, for example, the operating condition from velocity or from Mach, where you specify the boundary condition, the turbulent quantities, and you can also check the boundary names and the boundary condition that has been applied to each boundary. Same for turbulence model, where all, as I was saying before, all the coefficients are there reported, and the more advanced settings like the Jacobian, and the limiters, the low Mach preconditioner. Initial condition can be standard one, so from 0, or we can also fork from a previous run. Time stepping here, steady or unsteady, with ramp, and the type of output and the boundary by default are all, or you can also group the type of boundary that you want to output to, and of course the variable that you are using. Then this plot can be saved also and exported as PNG. You see there's a very nice tool to zoom in and to adapt as the solution progress. So you can actually pan, see, zoom in, and understanding where the solution is going. We also have some post-processing integrated in Flow360 to quickly visualize things and have an insight of what is happening. So in this case, just the CF surfaces of the car, and you can spin around, change the color bar, have the standard visualization tool. Is quite fast. It's all integrated in our platform. So in this case, you have the variable I choose in Python, but you can add as well your own variable. It's called user-defined variable. So if you have a variable that you want to plot, you can just write in the equation, and then it will appear in that list. Change, of course, the legends, saturate the bar, and so on. You also have, so this is the case that Jared showed before. You can see how smoothly it is. I'm running on my PC, so nothing fancy, but the mesh is still quite big, quite large. And here are as well slices, slices of predefined slices that you define before running. So then you have quickly show slices, or there are also pre-defined in the moment center, where you have usual XYZ in the moment with the variable CPT and ISO surfaces as well. We have so you see here ISO surface of Q criterion is quite powerful visualization tool. And that's it for me in terms of live, let's say, demonstration of what Flow360 is capable of doing. Now, let me carry on a case study that we did for EVs. So our so NIO is basically now using. There's a partnership with Flexcompute. NIO is is an EV company founded in 2014 and is basically the global leader in smart electric vehicle in the industry. The EV lineup including a sedan ET7 with a very, very low drag coefficient of just 0.208, as you see there, or an SUV. So it's quite a wide range of car. It goes from a small sedan to a very large coupe SUV, but even that with a quite low CD, because these are electric vehicles, so the drag is important for range. That's why their focus in NIO focus has been always on drag prediction. Now, if we look at what has been possible to achieve, NIO has choose Flexcompute after an extensive validation that has been done on their premises for more than 60 cases among different cars. So from small sedan, as I was saying before, to big SUV. And actually the numbers are quite impressive here in terms of accuracy, because more than 94% of cases are within the band of 3% delta to their wind tunnel test data. So our simulation tool has been proven very accurate on a wide range of scenario. Here you can see the the band, sedan, and the SUV there within the 3%. And apart from the accuracy, also is a substantially faster simulation. So respect to the previous CPU solution that was taking 10 hours, on 8L20 was less than an hour, so 10 times faster. But actually with our new H200 on 8 H200, so on the cloud, it can go also 120 times faster because it just run in minutes. So that's a very large improvement. Here, it completed a game changer for them. And it's not only on the aerodynamic part, but also the more challenging aeroacoustics part. Here you can see the focus was the windscreen noise and all the wakes and the shading done from the side mirror. And aeroacoustics is a very challenging branch because of, and very demanding, especially in EV, because of course there's no engine noise, and for the comfort, the wind noise is quite important. So this is the Q criterion around the side mirror and on the wake of the side mirror. And you see there the two microphones, so how we have compared to test. Really good agreement, always in our platform. So you also have aeroacoustics because the code is intrinsically compressible solver. So you have, let's say, the aeroacoustic for free. You don't have to run another simulation to get the aeroacoustics part. So this is a very big advantage of our solver. And the accuracy is very high for both the front and at the glass at the rear of this two microphone. You can see the spectrum. This simulation is a implicit LES, so it's not only so the code basically is accurate as well on very challenging from a numerical perspective simulation like an implicit LES. So this is words of Danilo Tebaldi, which is the principal chief engineer from NIO. I'll let you read, but basically says that it has been a game changer because of with the level of accuracy and the speed, they can make decision a lot faster and reduce the overall product development time. He has been very impressed by our solution, and that's why then he decided NIO has been now a partner with Flexcompute to choose our solution. In terms of what's next, so far is our solution. We aim to be an end-to-end solution, so not just the Flow360, the solver that you have seen. I briefly mentioned that we also have a mesher, but there will be also some other major release in 2025 to have the end goal will be having an end-to-end solution. And the objective of this is to have an ultra-fast, so aerodynamic solution that will give you as well for free, as I was saying, the wind noise, HVAC noise, and thermal. It's a multi-physics platform and a unified approach. I'm gonna handle back to Doug and then speak to you later if there are questions.
Okay. Thank you, Roberto. Thank you, Jared. Again, just to reemphasize, what Roberto just mentioned, so that the collaboration with NIO has been an important process for us. It has helped us to validate our product in an industrial environment. It has added tremendous value for NIO in terms of their ability to move quickly and to make decisions faster. And we're continuing to optimize that performance and add additional capability, as Roberto just described. Next slide. Okay, so with that, I want to thank everyone for their participation and attendance today. We do have questions that we've seen from the audience and that we will try to address here over the next few minutes. If there are additional questions, please feel free to put them into the Q&A of the Zoom webinar feature, and we'll try to get to those questions here in the next few minutes. Certainly, if there's any questions we don't get to today, we'll be happy to address them after the webinar. So with that, let me see what we have from the audience. Okay, so I think this is for Roberto. Flow 360 has shown significant speed ups. How does this translate into real world development time savings for automotive OEMs?
So this is a nice question. Thanks. So actually yes is a key, because the speed up that Flow 360 has is a key in the development cycle of an OEM. As Neo as well shown, and all our customers are showing, the development cycle in an OEM are very tight, and the ability of having an unsteady simulation in the time that you use to have steady case, that's the key of Flexcompute. It open up scenario that previously you won't be able to even think or simulate, and the level of accuracy that you have, it also reduce the time for you to go to testing. So it is a tremendous cost and time benefit.
Okay, thank you, Roberto. I think this was for Jared. How does subzone load on demand? How does the subzone load on demand feature in Tecplot 360 improve post-processing performance for large unsteady data sets?
Sure. Yeah. So the subzone load on demand, which you'll see as the .scplt file format when you load into Tecplot 360, Flow 360 outputs to this. And the way this works, as I showed in my slide earlier, the large volume data divided in smaller subzones, only the subzones that are needed for your plot are loaded in. And so for unsteady data, this carries forward where we're only loading the specific regions of each time step that are particularly needed for the plot that you're creating.
Okay, thank you. I think this one is now for Roberto. Can you explain how Flow 360 maintains high accuracy when they're doing large scale simulations, especially with compressible transient problems?
Yes, so the accuracy is guaranteed by the fact that we have, first of all, we can go on different type of scheme, and so the accuracy in general is the CFD inherently is dissipative. So to reduce the dissipation, we do have low dissipation scheme, and as well a combination of upwind and central scheme that sensibly reduce the dissipation of wakes, and that's increase the accuracy, because that's one of the major correlation issue when you look at CFD versus wind tunnel, is always that CFD tends to be more dissipative. The ability as well, one other issue is the separation points on, for example, cars that are not very defined separation point, like a sedan that is very smooth, so you don't have a defined line. To have the ability to tune the turbulence model and adjust the coefficient will give you that tuning capability to adjust the separation point and match the experiments.
Okay, thanks, Roberto. I think this one's for Jared. What are the biggest visualization or workflow benefits when using Tecplot 360 alongside Flow 360 for automotive applications?
Sure. Well, the big one is that the format Flow 360 outputs to is Tecplot 360 specific. I did mention that there is a way to bring it into FieldView, one of our other visualization tools, but Tecplot 360 is the choice when you're looking at SCL data. The other thing is that when you are benchmarking and you wanted to compare your results with other solvers, or if you have experimental results, Tecplot 360 has ways to load that data in as well. So it's good for comparison of simulation results. and you're going to get great performance when you're rendering this large data with SCL format and with our new graphics engine. It's going to be really good user experience when you're wanting to manipulate and load the plot and create the results you need.
Okay, thank you. What else do we have here? Okay, with growing, I think this is Roberto, with growing interest in unified multi-physics platforms, how are Flow360 and Tecplot positioned to support automotive challenges like air acoustics and thermal management?
Yes, so Flow360 and now I mean the integration with Tecplot is a key in Flow360 because as also Jared mentioned, the amount of data that we get, and we get this very large mesh. So when the code now is very fast. So we have seen that the simulation run now in minutes, an unsteady case or a DDS or a IVS run in hours. So that means that you have a larger mesh that you can afford now. So large mesh and larger cases. So all this means that the data management is a key. So to have a right post-processing tool that can handle smoothly this amount of data is definitely the key. And what Jared has shown us also with the improvement that are coming in Tecplot is definitely something that will make the user experience a lot better than what they used to. Area acoustics as well is a branch that that has a lot of data because it's intrinsically unsteady, and you have as well you need to have consider statistics and all these post-processing that are needed to analyze the acoustic field after an aerodynamic simulation.
Okay, thank you. One more question here. How accessible is Tecplot API for engineers who are newer to automation or scripting in their CFD workflows?
Sure. Well, you're going to have to know a little bit of Python, but the good news is the option to record from the Tecplot 360 user interface makes it a lot easier to get the PyTecplot specific commands recorded to a script early. We also have a lot of resources in our documentation for helping you get started, a lot of example scripts, and then our GitHub has example scripts as well to use a little more, pull in other Python libraries that you might want to use in your workflow. So we make it try to make it as seamless as possible for those who want to get started. But again, you're going to need to learn a little bit of Python, and you're going to need your own Python installation. But getting started with automating Tecplot 360 using that is pretty straightforward.
Okay, thank you.
Good question.
Okay, I think with that, we're going to close the webinar for today. We appreciate everybody's time. We're glad that you joined us. I hope you learned something valuable. Certainly, there'll be a recording of this if you want to download it in the future. And please feel free to go to either website for Tecplot or for Flow360 for additional information. And again, thanks to Jared and Roberto for their time and the information they shared with us. I hope again you found it valuable. Thanks again.